Hi, what is radioactivity? Well, that's the nature of this video. But before I discuss what radioactivity is, I'm going to give you a quick demonstration which models a little bit what Henri Becquerel did in 1896. And his discovery in 1896 is one of those serendipitous events. By chance and by accident, results came which then led to an amazing understanding of the nature, in this case, of radioactivity. Now, Henri Becquerel was interested in uranium salts such as this, and he was particularly interested in the fact that when exposed to bright light, a number of uranium salts were fluorescent, they glowed. And this was in the time also with Wilhelm Röntgen and his discovery of the Röntgen rays, or what you now know as X-rays. But one time he basically stored his uranium salts in the drawer within black paper to stop it being exposed to bright light. But at the same time, he also allowed it to come in contact with some photographic film. And when he developed the photographic film, he discovered that it was affected by the rocks or by the uranium salts. In other words, something was coming off the rocks that was exposing the film. And he correctly understood that the fluorescence and therefore also the radiation coming off uranium salts was something to do with the uranium itself. In other words, it was radioactive. And he came to that understanding, which then later, of course, with other scientists, including Marie Curie and her husband Pierre, discovered other substances that were radioactive. So what I have here is a Geiger counter. So I don't have photographic film, but I have a Geiger counter which will detect radiation. And I've got my little container of uranium salts. So I put it on and I press start, and you might hear the occasional click because in this room there is small amounts of radiation at particularly low level. But I actually suspect that these salts here are actually also causing this to trigger. So let's see if we can confirm that. So in that short space of time, it's picked up, well over 1,200 particles or something that is coming off my uranium salts. So the question is, what is radioactivity? Well, in this video, I'm going to discuss the three forms of radioactivity, also how they are different, and also the way that we actually write them down, so you know how we record the different types of radioactivity. So stay tuned. So before we start, let's give ourselves a working definition for radioactivity. And the definition I'm going to use is the spontaneous transformation of unstable nuclei into other nuclei with the emission of radiation. So for us to have radioactivity, we have to have emission of radiation. We have to also have the transformation of nuclei that are not stable into different nuclei that are more stable. And all of this is spontaneous. It occurs randomly and in an instant. So with that working definition, let's get into it. Now, before we start talking about why an atom may be stable or unstable, let's quickly review the structure of the nucleus. So here I have protons and here I have neutrons. And we know that we can make atoms by a combination of the number of protons and neutrons. So if I start with one proton, I have hydrogen. If I have two protons, I actually make helium, but that situation is extremely unstable. So in actual fact, helium has actually two neutrons as well. So we have a total number of 4 nucleons, that is protons and neutrons. That makes it stable. So you can see that we have equal numbers of protons and neutrons. If I add another proton, I'm going to get my next element in the periodic table. In this case, it's lithium, and we may be able to add another neutron to make it actually stable. Now, of course, I can continue this process along, and generally speaking, I need to have equal parts of protons and neutrons, at least in the lower half of the periodic table. Now, the question is, of course, why? Now, the reason, simplistically, at least at this stage of the video, is to say, look, there is a force that holds this together called the strong nuclear force that is overcoming the repulsive electrostatic forces that is pushing my protons apart. The strong nuclear force exists not only between the protons, but also between the neutrons and protons.
But in essence, what we're doing is we're just causing the protons to be far enough away so that the strong nuclear force overcomes any electrostatic repulsion that the protons have. Now, I have a video on the strong nuclear force and I encourage you to watch that. Now, of course, I can continue that process along by increasing the number of protons and increasing the number of neutrons. But that process, although generally we get a 1-to-1 ratio for a even number of protons and neutrons, so for example, carbon has 6 protons and 6 neutrons for the stable form of carbon, then if I keep that process along, we're going to find that at larger atoms, we're going to get greater need for more neutrons to remain stable. So if this here represents a graph that represents the number of protons and neutrons, so I'm going to have my proton number down the bottom and I'm going to have my neutron number over here, then if I were to plot on that graph there's certain number of stability situations where I have equal numbers of protons and neutrons, we're going to get atoms that sit along here. But as we go up, this line starts to deviate away. What it's saying is that for the larger atoms, I actually need more neutrons relative to the number of protons. So for example, uranium 238, which is written like uranium, like so, and then 238 up the top, this is the number of nucleons, so that's protons and neutrons, has 92 protons. Now you can see here, if I double this number, I'm going to get 184, and now I have a total of 54 more neutrons than the number of protons. So for stable uranium, that's the number we need for stability. Now, why am I saying that? Because if I have a radioactive substance, then my atoms are generally going to want to release nucleons in such a way that we get to a greater stability. That is the balance between the strong nuclear force and the electrostatic forces. So, for example, particularly large atoms here are going to be radioactive in a particular form, which we will call alpha decay, which we'll discuss shortly. For our smaller atoms, if the numbers are imbalanced, generally what they end up doing is beta decay, and we'll discuss this again as we go. Just one other quick definition we need to talk about. So here I have a carbon atom, and it is of course made up of 6 protons and 6 neutrons, so that will be 12. So now this is a stable form of carbon. But if I add 2 extra neutrons to this, then I'm not going to get exactly the same atom. However, it is still carbon because it's still got 6 protons. And now, because I have 8 neutrons, it's a number of 14. So this becomes carbon 14, and this one is radioactive. See how now we have more neutrons than protons, whereas we had equal numbers of protons and neutrons over here. So this is an isotope of carbon. Although we have some atoms in the periodic table which are naturally radioactive all the time, uranium is a good example, technetium 99 is a good example. For many atoms we have stable varieties and we have also radioactive varieties. And that's because of the balance of the protons and neutrons are such that it becomes less stable. That is, the repulsive forces between the protons is starting to be greater than the strong nuclear force, which is holding it together. And so you have various atoms with various numbers of isotopes. There are, in essence, 5 fundamental laws we need to follow to ensure that what happens remains true. And they are often known as our conservation laws. Now, the first conservation law you are familiar with, which is basically the law of conservation of mass and energy, sometimes written as LCE, but really we talk mass energy as combined. So it's the law of conservation of energy and mass. The second one is the law of conservation of momentum. But there are 2 forms of conservation of momentum. There is the linear variety, that is, if objects are moving in a straight line, but then there's also rotational aspects, which we call angular conservation momentum. Again, for our nuclear reaction to take place, our radioactivity to occur, these 3 laws ultimately have to remain true. There's more. The 4th one we have is the conservation of charge. That is, if I were to look at the charges of my radioactive atom and I look at the sum total charged substances on my other side of the equation, I'm going to have the same charge. We don't lose protons and electrons. We don't lose positive or negative charges. So we have conservation of charge. And the 5th one I want to talk about is about the number of nucleons. That is, the numbers of protons and neutrons on either side of our equation, the before and the after of my radioactive decay, has to remain the same. So if I have, let's say, just a random number, 150 nucleons in the before situation, I must have a total of 150 nucleons in the after situation. So let's apply that. So here you have my polonium-211, and it's unstable. That is, there is an imbalance in the number of protons and neutrons. And at some stage, what we're going to see is an alpha particle being emitted. There it goes. Now, this happens very quickly. In fact, it happens instantaneously. But the thing is that we can never ever predict when this is going to occur. It's a completely random event. So now let's have a look at many. And you can see that each alpha particle is emitted from the decay of each of the polonium atoms, and they are converting, or what we say, transmutating into different elements, that is lead. Again, all of this is completely random. It's instantaneous or spontaneous, and we can see the transmutation of one atom into another, and it's releasing these alpha particles. So here is a diagram of the example which you just saw. So what do I have here? Well, here I have polonium-211. Now, polonium has an atomic number of 84. And so in a correct way of writing this particular element is like this. So we have our element name here, we have our atomic number down the bottom here, and now we have our nuclear number, or often referred to as our mass number. But it can sometimes be written just simply with our mass number up top, because this is a bit superfluous. If it's polonium, this has to be 84, but we're going to write it down anyway so we can see what happens. This polonium decays into lead. Well, first of all, it's 207 because you can see I've now lost 4 nucleons. Down the bottom here, lead has an atomic number of 82. Now that accounts for this thing here. This is our alpha particle, and our alpha particle in essence is 2 protons and 2 neutrons. Now it's sometimes written like this. Why? Because it is actually a helium nucleus, but it can also be written like this. This is my alpha particle, but we put the numbers in here to show what is happening to our numbers of nucleons. You can see that I have 84 protons here, I have 82 plus 2 protons over here, so that's consistent. That's consistent with the conservation of our number of nucleons. Here I have 211 nucleons, I have 207 nucleons, I've lost 4, and of course 4 is the total numbers of protons and neutrons, so you can work out here how many neutrons we have. The one thing I haven't added is the fact that I'm going to also release a little bit of energy. Now, how much energy do you ask? Well, the energy ultimately comes from the concept called mass defect. If I worked out the mass of this polonium here in atomic mass units, for example, though I could work it out in kilograms, and then worked out the mass of this guy and the mass of this guy, I would find that the mass on the right-hand side of the equation is just a slightly little bit less than the mass I started with. Well, conservation of mass energy suggests that I have to have, therefore, a release of some form of energy. And here is that energy. And the total mass variation from the left to the right side will convert in terms of E equals mc squared into some form of energy. Now, how do we know that energy exists? Well, as you saw in my animation, this guy was shaking around and staying fairly stationary. And then all of a sudden, these two were going off in different directions. So sort of like a recoil. And so that gives both particles kinetic energy. And that's where that kinetic energy comes from. So that's alpha decay. So now let's have a look at our next one. Well, this is beta decay. So here now I have my hydrogen. And again, is an imbalance. I've only got 1 proton and 2 neutrons. And then suddenly you saw 2 particles coming off. And all of a sudden, I now have 2 protons and 1 neutron. What's going on? And as you can see now, a spontaneous event of a whole stack of hydrogen nuclei converting or transmuting into helium. And again, what we're getting are particles coming off. But if you look carefully, we get 2 particles all the time. Beta decay is where we have a different process going on. So here I have a small atom, and again, if I were to use the correct way of writing, I would write 3H and 1 here. Now that becomes helium. You now see that my nucleon number stays the same, and my proton number increases. Now what's going on here? Now what's happening is this neutron is transmutating. That's what we often refer to as that change into different substances into something else. In this case, it's become a proton. Now, conservation of charge means that because I've now gained a proton positive charge here, I need to release an electron as a result. And what this is. This is actually an electron, but we're not going to call it an electron, we're going to call it a beta particle. Now to be the numbers here to be consistent, we'll put a 0 there and we'll put a -1 there. And you can see I have a 2 and a -1 adds up to 1, so that's correct. Now, an important distinction, that this electron is not coming from the orbitals around the atom. It's coming from the nucleus. Was it there to begin with? No, it was not. So the electron somehow was generated by the fact that our neutron converted into a proton, but it didn't exist there for the first place. So don't get to thinking that my proton has an electron glued to it and it's removing off to form a neutron. That's not the case. Now, this conversion of neutron to proton is often related to one of the 4 fundamental forces, and it's often referred to as the weak nuclear force. Now, that's a different topic and maybe a subject of a future video. There is another form of this decay. This is called beta decay, but you can actually have this in a different direction. So if for example, I were to have the reverse reaction, so let's say I start with 3 and I end at 2 and I have a helium over here, and that converts to a hydrogen, that will jump of course to a 3 here, but now I've got a 1. So what's happened here? I've gone from 2 protons to 1 proton, and my number of neutrons has also changed because the total number remains constant. Somehow I've gained a neutron and lost a proton. Now that means I'm releasing some positive charge, and we write this like this. Notice the slight difference here. This is +1, this is -1. And this is called a positron, and it is a form of antimatter. So it's actually another version of beta decay, but it's actually referred to as a positron decay. Again, we have a transmutation of one of our nucleons. In the first one, we have a neutron converting into or transmuting into a proton, and in the other one, we have the reverse. We have a proton transmutating into a neutron. The only problem is this: both of them will release some energy, a much smaller amount of energy. Same principle. It's about the total mass on one side to the mass on the other side. So if we were to look at the mass over here, and look at the total combined mass over here, and these two will be such that the second one is smaller than the first one, and the difference in mass, often referred to as the mass defect, will give us the energy. But the problem with this is that the amount of energy here is significantly greater than the energy we measure of the beta particles after this. So somehow we're losing energy. And it was postulated by Wolfgang Pauli that there was another particle called the neutrino. And in the case of the beta particle, that is actually an antineutrino, and in the positron, it's a neutrino. And that was postulated to account for the variation in mass energy. And it was subsequently discovered in 1956. We've now discussed beta decay. The third one I want to talk about is gamma decay. And in this case, I'm just going to use the straight symbols. I'm going to use the symbol Tc for technetium. Now, technetium is a radioactive substance when it's technetium-99m. We won't worry about the M at the moment, but it has an atomic number of 43. Now, this particular technetium is radioactive, but it actually decays still into technetium-99, 43, but this is in a high energy state, and this is a low energy state. Now this is the subject of certainly another video, what the differences is here between high energy and low energy, but because we lose energy, we have therefore some form of photons of energy, and that of course is gamma radiation. So this is a form of radioactive decay that does not change the nuclear number or the atomic number, but is simply a release of gamma radiation. So how am I going to determine whether a substance is emitting alpha particles, beta particles, or gamma radiation? Well, how about I have a material here which I know is radioactive. It's sending out materials. And we've got a lead casing, so we're only getting particles that are heading in that direction. What we now want to do is place a magnetic field in front of it. So here's my magnetic field. You can see I demonstrate my magnetic field by just using crosses, so we know that the magnetic field is going into the board or into the page. And then what we're going to do is we're going to place a screen over here on the other side. And we know that this screen will light up if it encounters some radiation. So what's going to happen with my rays as they pass through the magnetic field? Can you predict that? Well, let's start off with gamma radiation. We know it's not charged, so it's going to pass through completely undeflected, and we're going to get a signal here. We know that that's going to be my gamma radiation. What about my beta particles and my alpha particles? Well, my beta particle, if it's at least a beta particle and not a positron, we're going to get it to turn. And why is that? Well, it's got a negative charge, and using your Lorentz laws and your right-hand rule or Fleming rule, depending on what rule you prefer, it's going to bend around. And it's going to bend dependent on the strength of the magnetic field, but it'll go circular until at such time it leaves the magnetic field. And so that's my beta particle. What about my alpha particle? Well, if you said it's going to go in the opposite direction, that's true. But it does not travel as far up on the board as the beta does in the other direction. Why is that? Well, my alpha particle is twice as large in terms of its charge, so the force should be twice as big, but the mass is significantly more than my beta particle. And this is an electron, remember, and this is 4 nucleons. So we are looking at about 7,200 times more mass than my beta particle. And so we're going to get, certainly it's not going to deflect as much. Now obviously the velocity is another factor here. So my beta particle may have a different velocity to my alpha particle, but needless to say, it's going to be less affected. So that's how you detect the alpha particle, beta particle, and the gamma radiation. Let's summarize what we've learned. Alpha particles, they decay in such a way that you start with a particular material, it has a particular atomic mass number and a particular atomic number, and it will decay into another material, it'll transmutate, but the mass number reduces by a value of 4, and the Z number reduces by a number of 2, which gives you an alpha particle, which can be written of course like this, or an alpha symbol, plus some energy. Your beta decay will look like this. You'll start with some original material, whatever that is. It will have a particular mass number and atomic number, but in this case, because we're releasing an electron over here, or a beta particle more precisely, then my mass number stays the same. But because now I have a neutron turning into a proton, the Z number will increase. And you'll have a little bit of energy, but remember, we'll also get an antineutrino. And of course, we have also our positron decay. And the last one, of course, is gamma. We have no change whatsoever, with the exception, of course, that we are releasing gamma radiation as well. So there's our 4 forms of radioactive decay. The spontaneous transmutation of an element into another element, and the release of radiation. The next question to address, of course, is that different substances do these things at different rates. And that leads us to the concept of half-life. But you're going to have to wait to my next video for that, so stay tuned. I'm Paul from High School Physics Explained. I hope that has helped you understand radioactive a little bit better. Bye for now. Thanks for watching. Please remember, like, share and subscribe. And by the way, drop a comment down below if the video particularly has been useful. And finally, consider supporting me via Patreon. The idea is to develop resources and equipment to continue to teach physics at a high school level. I'm Paul from High School Physics Explained. Bye for now.